I think we have completed all the combinational designs. We have started with our basic adders like half adders, full adders, and we have also seen our design, demultiplexer, encoder, decoder, and these are all things, all the combination circuits which we have covered in Verilog behavioral modeling. So let us start with the most important concepts like sequential design. Let us try to understand how to design these sequential circuits using Verilog in behavioral modeling, especially in behavioral modeling, right? So again, let us follow the same order which we have used in our digital circuits. Like first we have completed our combinational circuits and we have went to our sequential design, right? So now also we will do the same thing. We will start with our latches. Okay. So first let us try to build the basic latches. We will try to have latches, and after this latches we will go to the flip flops and so on. Okay. Now as we know, our latches is nothing but level sensitive devices. So latches are basically level sensitive devices, and basically this work on our enable signal. If our enable, so basically these latches are level sensitive devices, and this work on the enable signal. Whenever there is a positive level in your enable, then your device will work, or else your device is not going to work. Okay. So this we need to design. So we are going to design a basic SR latch, JK latch, D latch, and T latch. I am talking about latch, not flip flop. We are going to develop here these latches. We are going to start development, and we are going to also learn how to write the test benches for the sequential logic. For combinational logic, the test bench pattern was same, and for sequential logic, the test bench pattern is going to change. Okay. So we will see how to write the test bench for our latches and how to write down the test bench for our sequential circuit. We are going to learn now. So let us start with it. So we have created the same project I am going to do. Here I am going to create a file, add sources, create file, SR underscore latch. So this is my SR latch I am going to design, finish. Let me wait for the design to be created. Yes, SR Latch design file has been created. Let me open this. Now, let us write down the code for our SR Latch. So, inputs for our SR Latch, let me zoom in. So, inputs for our SR Latch are enable, reset, SR, and outputs are Q and Q bar. Okay. So, let us write down input, enable, reset, SR, and outputs are reg, Q, and Q bar are our inputs and outputs of our SR latch. Now, so I'm going to write down first of all the reset logic. And for this SR latch, I'm going to consider a synchronous reset. Synchronous reset. Now, basically we have two type of reset signals which we have already discussed in digital. So we have basically two type of reset signals. That is, one is synchronous reset and another is asynchronous reset. So in the case of your synchronous reset, we already know that whenever you apply the reset signal with respect to clock only, it is going to work. For example, if you apply the reset signal at your positive level of the enable signal, because we are dealing with latches, right? So if you apply this reset signal whenever whenever your particular enable signal is equal to high, then only your latch is going to be reset. If you apply reset signal over whenever your enable signal is equal to low, then your reset should not work. Okay, that is nothing but our synchronous reset. But in the case of your asynchronous reset, if you apply your enable signal, if you apply your reset signal, irrespective of enable signal, your reset is going to work and your design is going into a reset state. That is the difference between your synchronous reset and asynchronous reset. Now let us try to have a look how to design your synchronous reset and how to design your asynchronous reset. So coming to the synchronous reset, we are going to have an always at the rate enable. So whenever there is any change in the enable, this always block will be executed. Here we are not going to use star because your latch is only dependent upon your enable signal. If there is any change in enable signal, then only your always block should be executed and your device should be done. Okay. If enable is equal to 1, then if you apply reset, then your output should become 0. Q should become 0. Q is equal to 1 tick binary 0, and Q bar is opposite of Q, that is nothing but 1 tick binary 1. Okay. And since I'm using multiple statements here, I should use beginning block. Okay. This is my reset condition which I have written. This is my synchronous reset. Let me copy paste. This is my synchronous reset which I have written. Now, next what should I do? I should write down the logic for my S condition, set condition, reset condition, and one more is invalid condition and hold condition. Invalid we are not going to write. Okay. Now, so else if my S is equal to 0 and R is equal to 0, this is my hold condition. Begin. Q should be equal to Q and Q bar should be equal to Q bar itself. There should be no change in these values. Okay. And else if my S is equal to 0 and R is equal to 1, then begin. Q is equal to 0 and Q bar is equal to 1. Okay. So this is my hold condition. Let me write down. So this is my hold condition and this is my reset condition and this is my next. I'm going to write down my set condition. Else if S is equal to 1 and R is equal to 0, then begin. Q is equal to 1 and Q bar is equal to 0. Okay. So this is my set condition which I have written. Okay. Set and reset and hold conditions which I have written, and let us write down an invalid condition also. Invalid condition. So else if S is equal to 1 and R is equal to 1, then begin. Then my Q is equal to tick X, tick binary X, and my Q bar is equal to, let me write down it here, tick binary X. Okay. Tick binary X. Okay. And followed by end. So these are my set conditions and reset condition and invalid condition. Let me end this always block end and followed by end module. And always at the rate begin, I should write begin if enable, and if enable is there, then only all these conditions are working. Let me write down one more end. Yes. So this is my SR latch, and in this particular code, if you carefully observe, I'm using non-blocking assignments. I'm using non-blocking assignments when I'm developing my sequential circuits. So here in Verilog, there is a rule we should follow. For combinational circuits, for basically this combinational circuits, we should use blocking assignments. For combinational circuits, we are going to use blocking assignments, and for sequential circuits we are going to use non-blocking assignments. The reason we will discuss in the further course. Okay. So for the combinational circuits we are going to use blocking assignments, and for sequential circuits we are going to use our non-blocking assignments. Okay. Yes. So this is the code which we have written, and let me save this. Yes. So this is nothing but my SR latch. So if S is equal to 0 and R is equal to 0, this is my hold condition, and if S is equal to 0 and R is equal to 1, reset condition, and 1 0, this is my set condition, and 1 1, it is my don't care, that is invalid condition. So let me, yeah, save this, and what I will do is, first of all, let me write down the test bench. So how to write the test bench? Let me create the TB file for this. Create file TB underscore SR. Okay, finish. Let me open this file TB underscore SR, and here we are going to declare all the variables. The variables which we are going to connect with the inputs are declared as reg, enable, s, comma, r, and wire q comma q bar. Okay. And next step, this is our very first step. In the combinational design also we have followed this step. And second step is instantiation of our design. So let me copy the design name. So first two steps are the same things: declaration and instantiation. SR latch, and then design name is, let's say, DOT. Enable, and I think we have forgotten reset. Enable, reset, S and R. Enable, reset, S and R, and Q bar. These are our inputs and outputs which I am going to instantiate. Okay. Now, next is the third step. The third step also we already know, which we have seen in the combinational design, that is initialization of my inputs. So how to initialize my inputs? Enable comma reset comma S comma R, which is equal to 0. I have initialized my inputs. Okay. Next, after initializing your inputs, previously what we have done in the combinational circuits is we have just simply driven our inputs. Now in the sequential circuits, we are going to first generate our enable signal. Okay, we should generate our enable signal. Now how to generate the enable signal pulse? So like this, we need to generate our enable signal pulse. Like this, we need to generate our enable signal pulse. Now initially at t is equal to 0, your enable signal should be equal to 0. Let's say at t is equal to 5, your enable signal should be equal to 1, and at t is equal to 10, it should be equal to 0. At 15, it should be equal to 1. At 20, it should be equal to 0. Now, so what is the time period? The time period is this, that is nothing but 10 time units. It may be nanosecond or it may be millisecond. We don't know the time unit. Here we have the time scale as 1 nanosecond by 1 picosecond. So the time period is 10 nanosecond. Okay. Now, so for generating this enable signal, we are going to use a always block. How we are going to use always? Initially, your enable signal is equal to 0. After 5 time units, your enable signal should be equal to 1, and after 5 time units your enable signal should be equal to 0. Always begin and end. This is one way of generating your enable signal pulse. Always begin. Initially your enable signal will be equal to 0. After 5 time units your enable signal will be equal to 1, and after 5 time units your enable signal will be equal to 0, and again after 5 time units your enable signal will be equal to 1. So instead of writing like this, you can write like this also: always #5 enable is equal to not of enable. Enable is equal to not of enable. Okay, that means before that your enable signal will be equal to 0. At 5 time units your enable signal will get toggle, that is it is going to change from 0 to 1, and again 1 to 0. Like this your enable signal will toggle for every 5 nanosecond. Okay, so that is what I am going to write down here. So how to write it? Always #5 enable is equal to not of enable. Okay, always #5 enable is equal to not of enable. Yes, so we have this is the extra step which we are going to use in the sequential circuits. In the latches we are going to generate the enable signal, and in the clock, in the sequential circuits, we are in the flip-flops we are going to generate this clock signal. That is the extra step which we are going to follow in the sequential circuits, apart from the combinational circuits, compared to combinational circuits. Okay. Next step is we need to drive our inputs. How to drive the inputs? Initial, begin. So initially, first of all, we should apply the reset signal so that our Q and Q bar will be initialized. So reset is equal to 1. Okay. So you are applying your reset signal. Let's say here you are applying, here you are making your reset signal is equal to 1. Okay. Now at t is equal to 10, you can make your reset signal is equal to 0, or else at t is equal to 5 and 10, what is the middle point? It is around 7.5. You can make your enable signal is equal to 1 at the middle point. Okay, so I'm making my enable signal around at t is equal to 10 time unit. Okay, so what I'm going to write down is #10 reset is equal to 0. Okay, now next what I'm going to do, or else you can write this like this also: #10 semicolon reset is equal to 0. Like this also you can write it down. Okay. Next what we are going to do, so we have made our reset signal is equal to 0 at t is equal to 10 time unit. Okay. Now here we have made our reset signal is equal to 0. At the same point, you can apply your S is equal to 0 and R is equal to 0 or any condition, or after at this particular point, that is after 5 time units also you can apply, or anywhere you can apply. Okay. So what I'm going to do is I'm going to apply S and R signals at the same point at t is equal to 10. That is whenever I'm making my reset signal is equal to 0. So how to apply it? So simply write down S is equal to 0 and R is equal to 0. This is the very first condition which we are going to write down. This is nothing but our hold condition. Next what we have is our reset condition. How to write down our reset condition? Reset condition. So now we are not going to write down the reset condition exactly at the same time. Okay. So where we should write, so at the next stage we can write down our reset condition. And if you see, if our S is equal to 0 and R is equal to 0 was made to 0 at this particular edge, then there is a low level. Okay. Here these conditions will not work. We should wait up to this t is equal to 20 to change our inputs. Then only our inputs will be are going to work. Okay. So at t is equal to 20, I am going to give another set of inputs like S is equal to 1 and R is equal to 0. This is my reset condition which I am going to provide. So sorry, I'm going to provide a set condition. How to provide the set condition? After waiting for next 10 time units. Hash 10 S is equal to 1 and R is equal to 0. This is my set condition which I have provided. Okay. Now next what should I do? I should provide my reset condition. How to provide my reset condition? Reset condition. So after 10 time units, I'm going to provide my reset condition. S is equal to 0 and R is equal to 1. Okay, this is my reset condition. Now next what should I provide? The invalid condition I will get if I apply S is equal to 1 and R is equal to 1. S is equal to 1 and R is equal to 1. Okay. And yeah, so this is my code which I have written. Let me simulate it first and followed by end. Okay. And followed by end and end module. Let me save it. And let me make it as a top, set as top. Yes, so this is my waveform. Let us analyze our waveform, how it is going to look like. So this is my enable signal which I am getting. This is my enable signal pulse. Now this enable signal at the passage of clock, if I apply my reset condition, then your Q is becoming 0 and Q bar is becoming 1, as we know already. Now if we are applying S is equal to 1 at low level of your enable, it is not going to affect your output. Whenever there is a high level, then only you are going to get your output as Q is equal to 1. Whenever your S is equal to 1 and R is equal to 0, your Q is becoming 1 and Q bar is becoming 0. And whenever your S enable is equal to 0, then this R is equal to 1, your output is not getting affected. Whenever there is a positive level, then only if your R is equal to 1, your output is getting affected and it is becoming 0. Okay. And your output is becoming 1. And whenever your S is equal to 1 and R is equal to 1, your outputs are equal to don't cares. So this is how we are going to design our latches, all the latches: SR latch, JK latch, D latch, T latch. Okay. So depending upon the functionality and the truth table, we are going to see, and we are going to refer our enable signal truth table, and we are going to design. Okay. And here we are applying our reset signal till this up to how many nanoseconds? 10 nanoseconds. Let's say if I am deassetting my reset signal exactly at 5 nanoseconds. Let us see whether it is going to affect my output or not. So what I'm going to do in my test bench is, after 5 time units, I'm going to deasset my reset signal. Let me relaunch it one more time. So see, if your reset is equal to 1, but your enable signal is equal to 0, that's why your output is not getting to 0. Q is not becoming 0. That is, reset is not working because there was no enable signal, right? Now here also, if there is no enable signal, up to here there is no enable signal, and you are making your reset is equal to 0 immediately before the enable signal becomes 1. Okay, that's why your reset is not working. and your output q is equal to unknown and q bar is equal to unknown. Okay. Since this design is a synchronous reset design, your reset will work only whenever your enable is equal to 1. Now, coming to asynchronous reset design, this is your synchronous reset design. Coming to asynchronous reset design, how to build your asynchronous reset design? Let me come in this synchronous reset part. Coming to asynchronous reset design, simple. You can simply write here reset. That is, whenever there is a change in your reset signal or whenever there is a change in enable signal, this always block will be triggered, and this reset logic we should write it down. This reset logic we should write it above this if enable signal. Okay. Now let me explain you what is happening. First of all, let me come in this. Yeah. So what is happening here? In the case of your asynchronous reset, let me write down. It is your asynchronous reset. Whenever you are dealing with your asynchronous reset, then you are including the reset signal in the always argument. Then whenever there is any reset signal change or enable signal change, your always block will be triggered and you are checking for the reset condition. If reset is applied, q is equal to 0 and q bar is equal to 1. Previously, what was happening? Whenever there is change in enable signal, then only always block was triggering and it is checking for your reset signal. But now what is happening? Whenever there is any change in reset signal or enable signal, your always block is triggering and your reset signal is applied, then your output is becoming 0. Now, for this, let us check the output. Let me relaunch it. Let us check in the simulation what is happening. See, so whenever your enable is equal to 0, but you are applying your reset is equal to 1, your output is becoming 0, irrespective of your enable signal, whether it can be 1 or 0, you're not caring. If your reset is equal to 1, your output is equal to 0 and q bar is equal to 1. Okay, so this is the difference between your synchronous reset and asynchronous reset coding styles. Is it clear? Any doubts or any queries in this?